Hi, and welcome to the session for the Complete Treatment Entry-Level course about laboratory. In this presentation, we plan to explore some of the safety procedures, some of the lab techniques that are used commonly on a daily basis, weekly basis, and even talk about some that are not so common, all right? So we're going to start with talking about glassware. So there are lots of different glassware that are available to us in the lab, and used for various different things such as beakers, Erlenmeyer flasks, volumetric flasks, pipettes, burettes. But all of these have an inherent danger with them. First off being, we use autoclaves to clean our glassware and disinfect our glassware to get rid of samples. Well, coming out of an autoclave, there's nothing in this glassware that indicates that it's hot. So one of the safety procedures to keep in mind when using glassware is that this can often be hot and should be always treated as such that you do not get burned just in case something when handling these. Another thing is, these are glass. They can drop, they can break. So there's cut hazards associated with along this too. And another thing about glassware is that sometimes there may be dry residual chemicals on the glassware, and that when you're going to use it for titration or some sort of chemical reaction, there could be alternative reactions that occur and cause harm to an individual due to different gases that may be released, heat that might happen, explosions that could happen, and such along those lines. So just keep all those safety things in mind when using various glassware throughout your laboratory. So the very first thing we're going to talk about here is beakers. Beakers are used for transferring large volumes and carrying out reactions in these, okay? These are what we call graduated only for the fact that they have markings on the side for measuring, but these are very inaccurate when it comes to measuring. So we don't use these for specific measurements. We use them for vessels to carry out reactions, titrations, or transferring volumes of water. An Erlenmeyer flask is used for titrations of alkalinity, hardness, and pH. All right, these are very commonly used with a plate stirrer, and a heating element sometimes is involved with this. Then you have a volumetric flask pictured here. Volumetric flasks are not used for doing reactions in, rather they are used for measuring liquids. Volumetric flasks are calibrated with an etch amount and a set amount of volume that they are used to measure. So you're not going to use the same volumetric flask to measure 25 milliliters as you would to measure 100. You'll have different flasks for that because they are calibrated per the amount specifically, all right? And you're going to measure this amount by looking at what we call the meniscus, which we'll discuss a little bit further later on. The next thing to note is a pipette, all right? Pipettes are used for measuring and delivering specific measured small amounts of liquids to a reaction vessel, such as a titration or sample pipetting or something along those lines. Pipettes are the most accurate form of measurement used. And then we have a burette. Burettes are used for performing titrations. They allow a specific amount to go out. It's a very accurate, measurable amount with the graduations that appear on a burette. Burette looks like a combination of it has a test cock or stop cock at the bottom to control flow out of a dropper. So burettes, I often imagine them or explain them to people. They're a combination of having a pipette with a dropper end on it with a stopper and like a graduated cylinder that is used for measuring liquids. You can again measure by the graduations or measurement marks on the side by looking at the meniscus here. Burettes are also involved with having on a ring stand typically, and you often hear the reference to people in the lab, I have to pump it up. And what that's in reference to, a lot of times these have a like a triple tube on them with a feedstock chemical and bulb on them, where when you pump them up, it goes to an exact 100 milliliters. Because the amount of milliliters used for titrations is very important in using and calculating what you're titrating out, looking for hardness or alkalinity and such along those lines. So again, I already talked about this, but glassware safety is very, very important because, like I said, there's nothing on this glassware that indicates whether it's hot or not, like it could have came out of an autoclave. An autoclave operates at 121 degrees Celsius. Well, 121 degrees Celsius is much over the boiling point of water, over 200 degrees Fahrenheit. So they could be extremely hot, and there's nothing indicating it. So all glassware should be treated as if it's hot. Another thing with taking hot glassware and immediately exposing it to cold, it will shatter. And again, like I was talking, even dropping glassware will shatter it, which can cause different shards and different types of stuff that could cut you, all right? And then chemical concerns, like I was saying too. Sometimes the way these things are cleaned, there will be residual chemicals on the glassware itself, and the residual glassware or that residual chemical could create an unwanted reaction. And depending upon what it is, the reactions can vary widely, from creating excess heat, from explosions to creating toxic gases. It all kind of just depends on what it would be. So the reason why we do a lot of laboratory stuff is we're doing for monitoring. We're monitoring our disinfectant residuals, our pH, temperature, alkalinity, turbidity, hardness. And then other things that we're looking at is our concentration of calcium and magnesium, chloride and sulfate, and our fluoride levels. If we have this stuff present or we use this stuff, we're going to be looking at some of it on a daily basis even. Chloride and sulfate levels, because that helps, like we learned about in the corrosion, or if we haven't watched corrosion yet, sulfate and chlorides can affect the leaching of lead and copper, all right? The reason that we are required for monitoring too is most of these are done at complete treatment plants, and they are used for compliance, all right? Certain compliance samples can be run on site. Some you have to be a certified laboratory, and there are a number of our water plants that are certified for running bacteria samples, and that requires going through the lab certification with our lab certifiers here at the state. And what they do is they make sure that anything you are going to be certified to run and do, that you're following the standard methods procedures that are approved by the EPA, and they come out of the standards methods books. So one of the very first things we're going to be doing is looking at chlorine residuals. Chlorine residuals can be measured at various different ways, from DPD colorimetric, DPD phos titration, ampimetric titration, iodometric titration, iodometric electrode, which is only used for total, or as you can see here, syringilazine. So a lot of labs in Michigan, the two main ones that I know are DPD colorimetric and ampimetric titration. So we'll explore some of those coming up. So DPD colorimetric, as you're going to find that is true in lots of different methodologies and different medical terminologies, most acronyms refer to the chemical reagent that is used for changing color. So there's a couple different ones for DPD colorimetric. There's the color comparator, or what we call the color wheel. And then you have your spectrophotometer or colorimeter. That's a lot like the pocket ones. And depending if you're measuring free or total, things are going to change and how fast that you can read them. But DPD stands for N,N-diethyl P phenylamine diamine. Yeah, that's why we call it DPD for short. All right. DPD colorimetric, for looking for chlorine residual, there is two different types of tests to be done. There's the low range, which is typically from anywhere from 0.02 to 2 parts per million of chlorine. And then there's a mid range, it's anywhere from 0.05 to 4. And then a high range, which is 0.1 all the way up to 8 parts per million. So each one of these has a different type cuvette, has a different reagent / powder pillow, you want to say, with it. And the solution amount that is needed to be tested is different also. So a couple things to keep in mind with doing free chlorine residual: once you add the powder pack, you have to take the reading immediately or within 1 minute. Waiting beyond that 1 minute can cause interferences for the test itself. Now, if you're doing a total, this is going to have its own powder pillow with it. And the total chlorine residual, it takes about 3 to 6 minutes before you're able to read it. And the reason for this is because total chlorine is measuring any mono, di, or trichloramines that have formed, or any other chlorine complexes that have formed. So total is in reference to all of the chlorine constituents, not only looking at free chlorine available for disinfection. Now the blanks, like I was saying, for your low, which is the typical one we're taking out in the distribution system, it's typically a cuvette that it only holds 10 milliliters. On this cuvette, there's going to be a diamond, and you got to make sure that that diamond matches up to the read arrow on your pocket colorimeter or your D900 that you're running. And before we do any chlorine residual, you want to make sure that you have used that tube to blank it or to zero it, to zero the machine before you add your powder pillow, mix it up, and then add it back and take your reading. Now, again, if you're taking a mid-range or high-range, these are going to have their own powder pillows, sometimes 2, sometimes 1, and the amount of water needed or solution needed in order to do this is going to be higher. Typically, those are 25 milliliters, all right? So there's some QA, QC done, and what I mean by that is taking like every time you get a new set of powder, taking it and measuring the powder against a standard calibration that we know to make sure that it's within its factory reading. Another thing to be doing is with your pocket colorimeters, you should be making sure that they are properly calibrated. Again, this is done with standards that you order with the machine coming from the manufacturer of it to make sure that it is reading accurately. The manufacturer is going to include instructions that it should read between plus or minus point whatever it is for that machine, particularly for that test, because the test and the machine you're using for which method will change the acceptable accuracy to make sure that it's within calibration. And this is something that needs to be done quarterly or at least a couple times a year with your machines. All right, so now these are the different test kits that you can use for doing DPD colorimetric. The one on the right is a color wheel. The one on the left would be working on doing a pocket colorimeter. One thing that is often bad with color wheels, a lot of times these are left on the dash of a truck. The discs and plastic become faded that you use as a comparator. These color wheels are also to interpretation, and what I mean by that is people have different types of vision. So this just gives you a couple ideas of that. Now, here's some potential interferences you see. So with, like I was just saying, often with the color wheel, you get faded discs because they are left exposed to the elements and sun that fade it. If you have a bad light source, you're not going to get a good read because the colors will seem a little off. It's open to interpretation. Everyone's going to have a different interpretation of what that color shade is in comparison to the wheel. All right, and that's just variations in water. Other interferences is having colored water, like red water. Water that's high in iron is often to have some discoloration to it. All right, or even high in manganese will have some discoloration to it. It'll have like a blackish type faint to it, faint blackish tint. And then oxidizing agents. Ones that are high in oxidizing agents will react when reagents are added and can mess with the tint of it and the reading of it. Another thing too is, do we have expired reagents? So now with using a colorimeter, it's more expensive, it has more issues, but the thing about it, it is more consistent. Because with using a pocket colorimeter or a spectrophotometer, there is no open to interpretation, right? Some of the errors that you have with this, though, is making sure that the batteries are new and not corroded in it, making sure that the glassware is not scratched and is usable and readable, that the transmitter and receptor inside of it that are used to measure the color through it and do a measurement are properly cleaned and maintained and not covered in dust and so on and so forth. So this can always be zeroed out with a blank cuvette, and then you fill it, add your powder pillow, and there you go. Another thing about it is you got to make sure that your reagents are being upkept and they're not out of date. All right. So that's about really it. This doesn't need a test. The light source doesn't matter for this. Inconsistencies in vision has nothing to do with errors in reading on this machine. Here's just some picture of a pocket colorimeter up top. This is, I think, a D300. And this over here on the right is an online chlorine analyzer, where it is continuously taking reads of the oncoming water by taking like pull samples and taking reads of them. Now, this can't be used as a benchtop confirmation. You have to, in a lab, have your own benchtop verification for the online instrumentation to make sure that they are matching, because this might tell you which one is out of calibration, which one is not. Now, pH. pH, the only way that you can detect it is the electrometric method. And what it does is it measures the electropotential of the water and is able to determine the pH from that. So, some of the problems that we often see with this is making sure that these probes are properly stored. These are typically stored in either buffer solutions or DI water to ensure that the tip remains without having chemical residue on it and causing error inconsistencies in readings. It has an accuracy of plus or minus 0.1 units in accuracy. pH is the measure of hydrogen ions or hydroxide ions within the solution. If it's super acidic, it'll have a pH towards 1. If it's super basic, it'll have a pH towards 14. So these calibrations, typically there's a secondary check that you do on a daily basis to ensure that it is still within calibration standards. Plus or minus 5% accuracy is acceptable on these, but you have to do a monthly calibration with different standardization too to make sure that it uses. You're going to rinse before use this to make sure that any chemical is removed and there's no issues. Now, another thing is you're going to be using magnetic stir to ensure that the solution that you're measuring is consistent, that the acid is not all at the bottom or it's super acidic up top, that the solution is consistent with for being measured, all right? And like I said, typically the probes are stored in either a DI solution or a potassium chloride type solution, all right? We typically accept the 5% calibration. The standards that are used for calibration for these can be purchased from the manufacturer. They are typically a 4, 7, and 10. And then you have your electrodiode storage with these. These are available purchase from the manufacturer. You're going to make sure that when you get these and you open them, that the dates of record for opening and the dates of receiving them are recorded, because these solutions do expire after such a time, all right? So we want to make sure that we have current stuff that's up to date and usable, because if it's expired, it may not be very good. So when taking a sample, after that we've checked the calibration to make sure that it's within standard, you need to run the samples within 15 minutes of taking them, because the temperature of the sample can cause reading errors because it can affect the pH of the sample itself. Another thing that's very common with getting errors in the reading here is if you have your magnetic stir to try to make a unified solution up too hot, because if it causes an air pocket due to the cyclone within it, and the probe comes out of the solution, it's going to cause an error in the reading. So that's another thing to make sure that the probe is always submerged and not ever exposed to like an air bubble type scenario with the stirring. So temperature, we need to be using calibrated thermometers to ensure that the thermometer on the outside of an autoclave or on the outside of an incubator is completely accurate. Thermometers within an incubator, you're going to typically have 2 of them. They're going to be submerged. All right, and we'll talk about submersion or total immersion ones versus partial. All right, the reason for that is the immersion thermometers, they hold temperature variant a lot better when these incubators are open and closed. They don't have an immediate drop on the heat because of them being opened or closed, theoretically speaking. So the 2 types that we have are the partial and total immersion. You have graduations on these, and graduations, as I've stated before, are just markings that are there so that you can help indicate the actual temperature, like you can read it and get an accurate reading on them on what they are. Now, with reading them, you got to understand what the scale of the gradient is, or as they call it, graduations, because they could be from 0 to 2 degrees, they can be from 0 to 1, or they can even be further down to like 0.1 degrees, either dealing with Fahrenheit or Celsius. So you need to know the scale, all right? And that understanding that sometimes if there's a gap in the liquid because there's air present in that solution tube, that it may affect the reading itself, all right? So with temperature, we're going to be looking at temperature with calibrated thermometers, and typically thermometers have to be calibrated at least once a year. So if you're not going to check them for calibration or do the calibrations yourself, you can send them out to be calibrated, or you can simply buy new ones. A lot of people choose to buy new ones. A lot of times where we're going to see these is these incubators are these temperature thermometers are going to be placed as total immersion ones in an oil or sand immersion placed at the top and bottom of our incubators. And this is helping to ensure that our incubators are reaching proper temperature, because typically these are checked twice a shift, all right? So it reduces background interferences, and it actually gives you an accurate temperature reading other than just believing the digital thing on the outside of the incubator itself. Now in a lab, we use incubators. So incubators have a standard temperature of 35 plus or minus 0.5 degrees Celsius. They're used for growing bacteria samples. On these incubators, they range in various sizes. It's going to be depending upon the lab and the uses for them and how big they are. Typically, incubators too have 2 thermometers in them. They're total immersion thermometers, typically an oil solution at the top and bottom, and these temperatures are typically recorded twice per day. So they're going to keep records of every sample that goes in and out of this, time of when the sample was placed in it, who placed the sample, and what the sample is and where it's from. And then on that same logbook, when they take the samples out for reading, they're going to also include the results of the samples, whether they were positive or negative for coliform, or if it's an HP sample, HPC, we're going to talk about the number of colonies that was found at the reading time of the sample. They're also going to record temperatures twice a day in this logbook. They're also going to have a maintenance record book on this, and the maintenance record book is going to be any maintenance that's done to this, and it's also going to be about the calibration to make sure that it has been checked and calibrated to make sure that the incubator remains in specifications. The next thing we're going to talk about is alkalinity and the titration method. So an alkalinity titration is going to be using a burette for its titrant. So alkalinity, by definition, is the water's ability to neutralize an acid or resist acidic change. We talked a little bit about this in corrosion, but as a note, you cannot have a water with 0 alkalinity without it being corrosive. And alkalinity is required if you're going to be adding phosphate, because orthophosphate is typically phosphoric acid. It's the water's ability to neutralize or resist acid change. And along with that, the orthophosphate reacts with the alkalinity to form a physical barrier outside the pipe. So alkalinity is equal to the carbonate hardness of water. Typically, the titrants used for this are sulfuric acid or hydrochloric acid, 0.02 N. Normality sulfuric acid, or H2SO4, some know it as, is the typical. So a lot of times what they're going to do with this is they're going to use a pH-sensitive color dyes, such as phenolphthalein. And then there's a bunch of other ones after the phenolphthalein has been totally neutralized at a pH of typically 8.3. You're going to be using either methyl orange, bromocresol green. Bromocresol green methyl red is the typical. One that we see a lot of is bromocresol green methyl red is the typical one we see. Or you can also use metacresol purple. And what this is doing is measuring your P alkalinity, anything below a pH of 8.3. And then you use sodium thiosulfate before you begin your titration and adding your color dyes to eliminate the chlorine, because the chlorine, if not dechlorinated, can interfere with it, all right? So the P alkalinity, when we're getting down to the 8.3, is a measurement of our OH and carbonate hardness. or carbonate ion. So alkalinity, you have to be using a standardized acid because this allows you to make sure that the concentration remains consistent so you can get an accurate reading when you know how much and indicate how much acid was used. Compare dye indicators to the pH meter. So it's really important to make sure that our dye indicators are working properly and within standard spec. So it's typical to check pH with a pH probe just to make sure that it's working right and that it is doing and fading when it's supposed to while titrating. Compare the results between operators, right? Because another thing to be consistent with is your water, especially if you're using a groundwater, is going to be fairly consistent with the alkalinity that's there. But as you're titrating down, you need to compare that operators are getting the same number as far, because if not, someone might be overshooting the end result by adding the titrant too quickly. And then you're going to report your reading as calcium carbonate. All right. And as you can see, the titrants, typically you're going to have a mixing, this on a mixing stand, and it's done in an Erlenmeyer flask. All right. Some of the common issues with alkalinity is adding the acid too fast and overshooting that pH like I was talking about. Another one is the wrong acid strength. It might titrate down faster if you're using an acid strength that is unknown and unchecked. So that's another thing. That's why standardized acid is very important to use. You might have the wrong volume of sample. If you have the wrong volume of sample, it's going to require more titrant in order to get it down to where it's supposed to be. It might be failure to dechlorinate because chlorine can interfere with the reaction of the titrant. And then overshooting the endpoint. Well, overshooting the endpoint occurs by adding acid too fast. So that's very typical. Next analytical method we're going to be talking about is turbidity. Turbidity has a number of different modules that are devices that are used for calculating turbidity, but there is only one approved methodology, and that's the nephelometric unit. Typically, turbidity is reported as units as NTU, which stands for nephelometric turbidity unit, is what that stands for. So on the previous slide, that was a picture of the old method, which was using a candle passing light through a sample and using the human eye to read it. But nowadays, we have benchtop models that are used for confirmation. It must be taken every 4 hours. So your filter confluent must be taken every 4 hours because we need to monitor this, especially on surface water systems. If at any time you have a spike over 1 NTU on a surface water combined filter effluent discharge, that's going to trigger a boil water notice or a Tier 1 public notification. So we have benchtop units that are required to be in our laboratories to check at these types of systems every 4 hours. And then we have online turbidity meter analyzers too, which are also monitoring. These are typically located almost on every single filter, if not, and then in different places throughout the plant and at like your plant tap leading into your distribution system, because these have an online continuous read function. These need to be verified with a benchtop if these ever do have any spike in turbidity. But this just gives you a type of different idea for out there. There's a lot of different manufacturers for benchtops and online. There isn't per se one that's the gold standard. There are many different brands out there for measuring turbidity. So I guess we didn't really talk about what the definition of turbidity is either, but turbidity is things suspended in the water that scatter light as it passes through. That's kind of what turbidity is. So now you're going to be checking, you have primary standards, and primary standards can be a different thing. They come in a different range of stocks, but what these are what are used to do a primary calibration on your online analyzers along with your benchtop one. Each different manufacturer is going to have a different set of primary standards that you can get. Some use glass rods, some use the primary standards such as formazine. Some of them have gels that they use. They come in a set. It's very important to make sure that these are not outdated when using them to calibrate your machine. And typically your machine has to be calibrate it at least quarterly. Some places choose to do a calibration every month, but just to give you a heads up. So Formazine um, comes as a 4,000 TU stock solutions, but it kind of just depends upon what you're using. As you can see, Amco here has styrene, benzene, copolymer microbeads to use. I know Hach has different gel standards that you can get for primary, and so on and so forth. So it just kind of depends on what you're doing, but make sure that the stock is not outdated when doing calibration. That's one of the biggest things for primary. So secondary calibration, this is required to be done at least twice a day. Most people do it when they are doing their reads. So they take a secondary standard. So depending on the machine you have, sometimes the machines have to be left on or need a 15-minute warm-up period. Some of the newer machines from Hach that are laser don't require a warm-up period. They can just turn on and they're good to go. With doing this, a lot of times before they run their standard or their sample, they will put in their secondary standard to make sure that the machine is within calibration. Again, these come in different types from different manufacturers. Some of them have multiple different standard secondaries that you can use for calibration. I know that it says we're looking at a 15% tolerance, but I will tell you the acceptance standard is typically 10%. So like if you're using a 20 NTU secondary standard, it has to be within 2 NTUs, meaning anywhere from 18 to 22 would say that it's within calibration. There are some that have a solid state secondary standards, like a glass rod, but we typically don't recommend them because it doesn't take much to throw the calibration off of using that glass rod. So it depends on your manufacturer, but every manufacturer is going to have secondary standards that are used on a daily basis, at least twice a day, if not more, to check calibration before you're taking your every 4-hour sample and calibrating, or to make sure that it's within standard rate. So that's kind of what you're looking at with turbidity. So the next thing we're going to talk about are some things that cause interferences. So now with turbidity, there is these cuvettes. We're going to use cuvettes for them. So depending on like the new Hach units. So the Hach units, some of them use a laser now. Some of your older ones, if you still have an older one, the cuvette itself has a diamond within on the shape of the glass. That diamond is supposed to be lined up with the arrow inside the turbid meter. And some of your other manufacturers are the same way. Their cuvettes need to be lined up with their read function. The glass is built so that it is read at a particular range like that, whereas the new Hach ones are read from the bottom using a laser. So there's like Lovabond, there's Hach, there's a few other units out there too that are approved for use. So there are some interferences that you deal with. Sometimes these glass cuvettes have scratches on them. Well, you use a Kimwipe and silica oil to sometimes that's able to fill minor scratches and allow an accurate read, but that's one of the interferences. Another interference that could occur is having air bubbles in the solution. One way of getting rid of an air bubble in solution is use like an ultrasonic bath, like a water bath that has ultrasonic in it because it vibrates the bubbles out of air, or sometimes tapping it, but be careful with that because tapping it on the table like a lot of people do can scratch or even crack the glass. So the read will be inaccurate. Another thing to do is like cold samples. You might have to put the sample in a water bath to bring it up because you might get condensation on the outside of the cuvette, which will read inaccuracies too. So always try to wipe down these with a Kimwipe. Try to avoid fingerprints because fingerprints on the glass will cause errors in reading too. So those are a few of the interferences that we typically see. Now, continuous read units are exactly what they say. You're going to typically take your primary and secondary standards of a continuous feed to make sure that the device itself is within calibration standards. Typically, they're checked monthly with secondaries and quarterly with primaries to make sure that they're completely recalibrated. And again, like this, you're going to double check your results with it against your benchtop if you have any reading errors, just to make sure that it is accurate. And like I had mentioned earlier, typically we say 10% accuracy plus or minus is what we're looking for. And when comparison to that of your benchtop unit or even your standards when doing calibration. we're going to talk about is hardness titrations. So our plants that run surface water are required to monitor the amount of hardness, and so, some of our limited treatment softening plants will also want to monitor their incoming and outgoing hardness to make sure that their ion exchange is working. So the hardness is going to be looking at our raw incoming water and our water leaving the plant. Hardness or total hardness is the equivalency of your carbonate plus your non-carbonate hardness. But if you remember, carbonate hardness is equal to alkalinity that we talked about earlier in that titration. And in order to determine how much hardness it's done by calculation, by knowing how much of your titrant you used. And in this case, titrant for hardness is EDA or EDTA, which is the titrometric method for doing titrations with this. So when doing a titration for hardness, you're going to be adding a few things, a color indicator to it, a buffer, and some magnesium chloride added to the water, all right? And that again acts just as like another type of buffer to it. So the color indicator we're going to be using is Aerochrome black tea indicator. And as you can see here in the picture below, it starts out as like a pinkish reddish color, and then it's titrated down to a blue color, right, endpoint. So as they continue to add the titrant to it, it changes color and it moves down through. And as the color changes, this gives you your endpoint. And then you use a number of milliliters in the titrant in order to determine how much hardness there truly is in your sample. The thing we're going to be looking at is measuring fluoride. And there's a bunch of different methodologies that can be used. There's ion chromatography, ion selective electrode, Spadons and Spadons 2, which is a new method approved by the EPA that we'll talk a little bit about, but for most, it's the same as Spadons. It's a little bit less harmful and has a little bit less risk to it. So the ISE method is typically what is used in most bench tops that are used at water plants laboratories, and the reason being that it's very accurate, it's very simple to use, and it takes a little bit of readability error out, and it has less interferences. But it consists of a meter electrode, a reference electrode, a magnetic stirrer, and a hot plate to mix the solution. So with doing the ISE method, ion selective electrode, you have to put a buffer solution in there to adjust the pH to 5 to 5.5. This will adjust it, and this helps in creating the brackets needed for your range and your slope for detection. It optimizes the ion availability. It's typically a 1-to-1 ratio depending on the amount of sample or the TISPA used. It just kind of depends which one you're using. Typically, your calibration standards are going to fall in your curves of 0, 0.5, 1, 2, and 4 milligrams per liter. And that's because these are the typical ranges for drinking water. Now, if you're doing a raw water sample from somewhere known that has very high fluoride concentrations, you might have to adjust that bracket when doing so. But when doing the methodology too, you have to allow time for the electrode reading to stabilize before recording it, because it may jump around a while while it's stirring the solution together and stabilizing. So you got to give it some time in order to do that. All right. And another thing is to make sure that the pH can be used with the stirrer and the electrodes that you're using, because the pH being adjusted down to 5 to 5.5 makes it an acidic solution. Some of the pros to this, it gives you a greater range depending on the brackets that you set up and use for your calibration curve, but it's anywhere from 0.1 to 10 milligrams per liter parts per million. There's fewer interferences with it because they form ion complexes with the TISPA added to adjust the pH, so those complexes don't come through as interferences in the reading technology itself. And there's less technique errors. There's only a couple things to do, and then you allow it to just stabilize and take a read. Though the reason why some water plants choose not to do it is because it's more expensive and there's more equipment to maintain. Because when the probe's not being used, you do have to ensure that it is being stored properly in the right solution to ensure that it has proper functionality in the future. Typically, these are in DI water, because they're being ion selective. If they're in an ionic solution, it could interfere the reads in the future. The next method we're going to be used to talk about for measuring fluoride is Spaddens. Spaddens is a very commonly used method. It's a lot cheaper and it uses a pocket colorimeter that very similar to that of for chlorine. Spaddens is an acronym because it stands for sodium 2-parasulfonyl 1,8-dihydroxy 3,6-phenylene disulfonate. That's why we call it Spaddens. It's a colorimetric method very similar to DPD colorimetric used for chlorination, where we add this reagent and it forms a zirconium complex with the available fluoride. Well, in order to accurately get a fair measurement, you have to distill the sample and dechlorinate it upon using it. Spaddens has a very limited shelf life, meaning you got to make sure that your reagent is within its specification and being allowed to be used, and that it's not outdated. And if the sample is more than 2 parts per million, it will not read accurately. So you have to do like a drop dilution type method in order to get it to work. So if the reagent is added and the sample is a lighter color, that means that there's more fluoride. The lighter the color, the more fluoride there is. All right. So one of the things with the dechlorinating agent that is used in the Spaddens method is sodium arsenate. Sodium arsenate is used because sulfate can cause an interference in this. So that's why they don't use sodium thiosulfate in this, is because it could cause an interference. So they use sodium arsenate to dechlorinate the sample, which means it contains arsenic, which means it is a possibly harmful chemical. You must dilute it if it's over 2 parts per million. That's another con to this. There's a lot more interferences, especially if the water is not distilled. Some of the interferences you deal with are aluminum, iron, different phosphates, and different sulfates can cause errors in the reading. A lot of times they decrease the reading, meaning it indicates it has a smaller fluoride value than it actually does. The reason why this one's often used, though, is because it's less operator training and it's cheaper. And the unit that is used for this is a lot cheaper and takes up a lot less room, too, than that of the Spaddens original method. But there's a now Spaddens 2 method where the color reagent itself and the chlorinator does not contain any harmful arsenic in it. So the technique is very similar to Spaddens 1. It's just the chemicals and reagents used does no longer contains arsenic, so there's less of a concern for the hazard and safety to the user that this is being used with. The next thing we're going to talk about is autoclaves. So autoclaves are used to clean your glassware, used to destroy any biological samples that may have been used. All right, it sterilizes them, and it can be used to sterilize some other samples too. And so the main function of it is, though, to clean and make sure that glassware is safe to be used. So it sanitizes glassware at 121 degrees Celsius at 15 psi. It typically runs anywhere from 15 to 30 minutes. It just depends on the contents that are put in there. So you're going to keep a record logbook on this machine, sort of similar to that of an incubator. That's going to indicate the samples that were being put in there to be sterilized. That's going to indicate the glassware. It's going to indicate the runtime and pressure, and did it pass. And there's also going to be a thing in there, record sheets, to make sure that it's any maintenance that's been done to it. You're going to be tracking the maintenance on it and that's been performed to it. So typically when you go to fill this and run an autoclave, you're going to put an indicator in there. It's typically like a white piece of tape, or it looks like paper, and that thing will completely dissolve if it reaches the proper temperature and pressure, which indicates as a double check and quality check for when you're pulling the samples and glassware out to ensure that it did what it was supposed to do at proper temperature and pressure. So the next thing we're going to be talking about is a quantitative bacteria method known as heterotrophic plate count. So there are different things that you can do, like SimPlate and stuff like that. HPC is the most commonly used method. And what it is HPC, heterotrophic plate count, is used because it gives you an indication of the bacterial load that your water system may have in it. The test uses a non-discriminatory food source, unlike CoAlert and CoAssure and CoAtag that have a food that is only used by coliforms and then E. coli, the food that is used for HPCs can be consumed by all bacteria. So when we run an HPC and we get growth on the plate, it's only indicating that the amount of bacteria that's there. Hopefully we get none, but if it indicates there's lots there, well, this method is sometimes required, especially for those who utilize a surface water plant. And we're finding very low disinfectant levels out in the distribution system. An HPC is required by law to be taken and looking to see what the bacteriological load may be out in that part to ensure that we have proper disinfection within our distribution system. That is absolutely vital. So HPCs, that's what it is. It involves using Petri dishes and a non-discriminatory food source, or agar or auger, however you pronounce it, that will allow any bacteria to grow. So with a heterotrophic plate count, again, it uses non-discriminatory food to detect the amount of bacteria there. So you can buy pre-made agar where all you have to do is melt it in a hot water bath. Typically, the hot water bath is anywhere between 44 and 46 degrees Celsius. And you're going to need enough for 2 Petri dishes. So typically, it'll be 2 test tubes of this. Some water systems and labs are big enough that they do this enough where they make their own media, which is even cheaper. But a lot of them choose to make and buy pre-made media that needs to be melted and prepared. You're going to get 2 sterile Petri dishes. One's going to serve as a control, and one's going to have your sample in it where growth will occur. If growth occurs in your control sample, then you're going to have issues. That means that the test was not done properly. So what's going to happen is you're going to open the Petri dishes. You're going to add 1 milliliter of a sample out of a BACT sample bottle onto a Petri dish, and then you're going to add the tempered agar, which means it's melted. You're going to add agar to both of these pour plates, and then you're going to swirl them on a flat surface in a figure 8 type method. And that figure 8 method is going to spread it evenly out across the plate. Then you're going to place the lid back on the plates, and you're going to let it solidify. Once the agar has solidified, you're going to invert them, both of them, place them in a plastic bag, and then place them in the standard bacteria incubator, which is 35 plus or minus 0.5 degrees Celsius at 48 hours. And then the readings are going to be taken at 48 hours. When we do, if we have colonies, when we count them, they were reported as CFUs per milliliter, which stands for colony forming units. Hopefully, when you pull your control or you pull your bag out at 48 hours, there's no growth in your control. If there is growth in your control, that means the sample is going to be invalidated because there is some sort of contamination within the media or within doing the test itself. So we're going to take this thing to a Quebec colony counter, which you can see here on the next page. So here's a Quebec colony counter, and what this does is it helps create quadrants to count the bacteria colonies on an HPC. It has a backlight to it in this gridded pattern so that you can count them in a certain number of square, and then you use the most probable number to come up with how many colonies there would be there. Well, a lot of times when doing HPCs, we come back with very, very few colonies, if any at all. So as I was indicating, by law, any surface water treatment plant that has anywhere in their distribution system that the chlorine disinfectant level drops below 0.2 parts per million is going to be required to run an HPC, because we want to make sure that even if the disinfectant level is low, it's still doing its job. So if we do a colony count and it's under 500, that means that the disinfection is doing its job properly, even with a lower amount within the distribution system. Last few things that we're going to be talking about is the bacteriological methods that are approved. There are a couple other ones that are not listed here, but these are the 6 most common approved ones and used here in the state of Michigan. Firstly, an enzyme substrate reaction, being CoLalert, CoLaSure, and CoLaTag. And the reason they're called enzyme substrate is there are very specific food in these that can only be consumed by coliform bacteria and then can only be consumed by E. coli. This methodology was kind of born out of the multiple tube fermentation and presence-absence tests, but it was later refined into being these enzyme substrate reactions. Then we'll talk about multiple tube fermentation, membrane filter, and then presence-absence tests. All right. So the first one we're going to be talking about is CoLalert. So Kohler is an enzyme substrate reaction, is probably the most commonly used bacterial method in most of our water plants. So how this starts out is you have a 100 milliliter sample, requires at least 100 milliliters. The sample bottle will be dechlorinated because there'll be sodium thiosulfate within the bottle. The bottles before the sample is taken need to be sealed. If you go to take a bacteriological sample and the bottle is not sealed, you should not use it. Throw it out, get a new one. All right. So you get a 100 milliliter sample of water, and then it is brought to a cooler to your certified lab. In order to run any of these bacteriological methods and be approved by the state or accepted by the state, they have to be in an approved, certified laboratory by the state of Michigan. There's a list of those on our website. So what you're going to do is you're going to take a 100 milliliter sample. The lab is then going to add the powder pack of Kohler media to it. They're going to shake it up till it fully dissolves. The water was clear and will have a little bit of a cloudiness tint to it, but nothing too significant. Then it'll be placed in the incubator for 24 hours. And then if they pull it, the laboratory pulls it out. The incubator has a 35 plus or minus 0.5 degrees Celsius. And after it's sat in there for 24 hours, the laboratory pulls it out for analysis to see if it's positive for coliform and then E. coli. So they have a color comparator that comes with the stock of media when you receive it from the manufacturer at first. Now, if the media is less than the color comparator, so it has a slight tinge of yellow, but it's not as dark as the comparator, the lab will place it back in for no more than 4 hours into the incubator. If they pull it out at a maximum of 28 hours and it still hasn't changed darker than the comparator, it's considered negative for coliform bacteria. If they pull it out and there's nothing at 24 hours, no color change at all, it'll be considered negative for coliform bacteria. If it's negative for coliform, that means it's negative for E. coli. But if the sample is yellow and darker than the comparator, we consider that presumptive positive for coliform bacteria. Now, to check whether it has E. coli in it, the laboratory is going to put it under a black light with a certain frequency. The black light with a certain frequency will cause the media to glow a blue fluorescence. And it's quite obvious when it's positive for E. coli. So they're going to test this and then report back to you with this. So it is clear upon initial, yellow for positive coliform, and then a blue fluorescence for E. coli positive. All right. Now the next one we're going to talk about is ColiSure. So ColiSure is manufactured by the same manufacturer of Kohler, but it's created because Kohler can have interferences if you have yellow tinted water or water high in iron. So when ColiSure is added, again, this needs 100 mLs, and it's added, it turns the sample yellow initially. So if the sample remains yellow, then that means there's no coliform present. This is read at 24 hours. Again, if there's a slight color change, but not a ton to the comparator, it can be incubated up to 48 hours to see if you get any additional color change in the sample itself. It's at 35 plus or minus 0.5 degrees Celsius again. And this turns a magenta color when positive for coliforms. And then you'll get a blue type fluorescence again under a black light. So to indicate if it has E. coli. So it's yellow with nothing, magenta if it's positive. So that helps with that yellowing interference of iron that may be present in the water. And then blue fluorescence if it's positive for E. coli. So Colitag is an enzyme substrate reaction, specifically for E. coli, again, just like the other ones. It requires 100 mLs. The presumptive positive, meaning after it's been incubated, is yellow, and it will produce a blue fluorescence under a black light. This can be incubated anywhere from 16 hours to 48 hours and read at any time, and compared to the color comparator within that, has to be incubated at 35 plus or minus 0.5 degrees Celsius. So the reason that this can be read at 16 hours and not 24 is if you choose to pre-warm the sample. So the procedures for that can be found in the test, but if you take the sample, inoculate it with the powder, and then place it in a hot water bath, I think for up to 30 minutes, once it's in that water bath, you can accelerate the time that it takes to read whether there's coliform bacteria in it at as little as 16 hours. It is the fastest method on the market, so to speak. Next one is multiple tube fermentation. Multiple tube fermentation is kind of a thing of the past. It's not used all that often anymore because multiple tube fermentation, by the time that you go through all the steps of doing it, can take anywhere from 3 to 5 days to get an accurate reading whether there's bacteria there. So this is a broth-based testing method where you take your water sample and you enter it into what we call a Durham tube type media, where you're going to get color change and air bubble formation in this vacuum air Durham tube in the first step. If we have gas formation or color change within that, that indicates that there's coliform bacteria there. Then after that, you're going to take that sample, meaning that it has it, and run it in a multiple tube set of up to 10 tubes, looking to see after if there is multiple bacteria in this thing. And as you can see, the sample gets diluted from one tube to the next tube to the next tube to the next tube. You get it 24 hours of incubation, put it under an ultraviolet, and when you do so, you're looking for coliforms and E. coli, and then you use the most probable number to indicate whether you actually have E. coli or not. Membrane filter. So there are a number of plants that use this. So what this is it's a filter plate based method. You take 100 milliliter sample, is passed through a very fine fiberglass filter that captures bacteria. It has very small pore sizes in it. The funnel is rinsed with additional, after you run your first sample through it, you rinse the funnel with additional distilled water to rinse any bacteria that might have got stuck to the side of it down onto the filter. This filter is then placed in a petri dish that has an agar in it, and the agar will allow bacteria to grow. This is measured at 24 hours, and you're going to be looking for certain types of colonies at 24 hours. It's incubated at 35 plus or minus 0.5 degrees Celsius. And when we pull this out to read it, we're looking for colonies that have a blue, green, metallic sheen to them. It is very obvious. You can see, like this one's here in this picture, there is a metallic sheen there to that. If it has a blue or green metallic sheen to it, that isn't coliform colony. So if it's found that you have coliform, then you have to isolate that colony to see whether you're dealing with E. coli or not by using another testing method. All right. The number of bacteria can qualitatively and quantitatively be determined, because this is sort of like an HPC, but on a smaller degree, and it specifically looks for coliform if need be. The next one is presence-absence. So multiple tube fermentation and presence-absence kind of were combined to give you color and those substrate reactions. So this again is a food broth media where it starts out as like a purplish color and then turns yellow if it's positive. So you take your 100 mLs, you add the food broth to it, you stir it up, throw it in an incubator between 24 and 48 hours. So if you have a slight color change at 24, you put it back in for an additional up to 24 hours to read the sample. In this, you're going to be looking for it starting out as purple and then turning yellow if it's positive. And what this does is it helps eliminate any interferences with having iron and stuff. And this literally only tells you whether you have coliform bacteria or not. It does not indicate whether you have E. coli within your system. An E. coli confirmation step is needed. Typically, you'll use another methodology to determine whether there's E. coli or not in this. All right. So without any questions, feel free to reach out to me anytime. Thank you and have a good day. Thanks for watching.